Dr. Ranjini Parthasarathi is a professor in Department of Computer Science and Engineering. Her area of specialization is in computer architecture and computer networking. She had guided more than 5 PhD students and currently guiding 5 PhD students. She had published papers in more than 50 national and international journals. She worked in many sponsored projects and she got IBM Faculty Award for 2008.
Welcome to the UGC lecture series in computer science. The broad topic that we are looking at is networks. Today's topic will focus on physical layer. So let's look at what our learning objectives are for today. We will be looking at the physical layer and understanding ideas on data and signals. The second thing we will look at is understand the issues that occur at the physical layer and the solutions for those issues. So if you look at the physical layer, we know that the fundamental job of the physical layer is to convert data to signals. So, and these signals will propagate down the medium along the link. This is what happens in a physical layer. When this happens, there are certain issues that occur. So what are the issues? They are that a delay can occur during the transmission. You could have noise present which will hamper the transmission or which will interfere with the transmission, and you also have attenuation of signals. Now we will look at these 5 points a little bit more in detail. So let's first take data and signals. What do we mean by data and what do we mean by signals? Data is the information to be communicated. Now this data could be analog or it could be digital. Now when you talk of analog data, we have audio. Examples of analog data would be something like audio, music and so on, or video. Wherever there is an analog information that needs to be transmitted, we refer to that as analog data. If you look at digital data, binary data, ASCII files and so on, they will all give you examples of digital data. And what is that signal? A signal is the carrier of information. So data is information to be communicated and signal is the carrier of information, and again the signal could be analog or digital. Now let's come to this analog and digital a little bit. So what do we mean by analog signals? So analog signals are those signals where the amplitude changes continuously with time with no discontinuities. As we can see in this figure that's given over here, there are no discontinuities that you have in this figure. You have that as time goes by, you can see that the amplitude changes continuously. It takes different values, but continuously there is a change in the amplitude. So amplitude changes continuously with time and there are no discontinuities. This kind of a signal is referred to as an analog signal. And what is a digital signal? A digital signal will have discrete amplitudes and it maintains constant amplitude for a prescribed period of time and then changes to another level. So with respect to time, we are defining these two quantities over here. Analog signals, with respect to time, the amplitude is varying continuously, and digital signals with respect to time, it takes different amplitudes. Time wise there is a continuity, but with respect to the amplitude, it is either continuous or it is discrete. This is the distinction that we have here in terms of analog versus digital signals. Now let's look at digital signals. So what does a digital signal look like? A digital signal can have, as I said, it has discrete levels. Now the discrete levels may be just 2 levels. So you can refer to it as a binary signal as shown in the figure over here, or it could be with multiple levels which is shown in the figure below, and when you have digital signal with multiple levels, we refer to them as ternary signals or quaternary signals depending on how many levels are used. So in a binary signal you only have 2 levels. So one level which represents say a value Vmax and another level which represents a value Vmin. Whereas when you have multiple levels, then you have V1, V2, V3, there are 3 different levels that are represented in this kind of a signal. So now what happens is, when you have 3 different levels represented, then it's called as a ternary signal. If there are 4 levels like this, it may be referred to as a quaternary signal. So you have digital signals here, where you can see that the amplitude is changing. There are discrete values that the amplitude takes at different points of time. So this is what we have in terms of a digital signal. So now we understand what is meant by an analog signal and what is meant by a digital signal. Okay. So now when we talk of analog signal, digital signal, analog data and digital data, there are 4 different possibilities that we get. So what are these 4 different possibilities? You can have analog data being converted to an analog signal, or you could have digital data being converted to an analog signal, or you could have analog data being converted to a digital signal, and the 4th possibility is digital data is being sent as a digital signal. That is, on the data side we have analog or digital, and on the signal side we also have analog and digital. So what happens in analog data, analog signaling? That is, the data itself is in the form of an analog information, and that is being transmitted as an analog signals. An example of this is what we find in our radio transmission, that is, we hear to AM, FM radio and so on. In all these cases, what is it that we are hearing? We are hearing audio. Audio is already in an analog form, and the signal that is used to carry this analog data is also in the analog form. So we say it's an example of analog data, analog signal. Now we'll come to what is AM and FM a little later, but you can take this as an example of the first category, which is analog data, analog signal. Now the second is digital data, analog signal. Now we know that whenever we have, let's say we are using a telephone for communication. Now again, when you use just a telephone for communication, suppose I am talking on the telephone. When I talk on the telephone, again the data there is analog because I am talking just voice. That is again just converted to analog signals, electrical signals, and those analog signals are carried as such on the telephone wire. So it's an analog signal that carries the analog data. So that also is an example of analog data, analog signal. But on the other hand, if I use the telephone line to carry, say, data, for instance, I have a computer connected to the telephone line, and I am now going to send data from the computer, say a file, through this telephone line. Now the telephone line is going to carry an analog signal. The signal actually will be analog, but the data it's going to carry is digital. So that is an example of a digital data being transmitted as analog signal, and we need now devices called modems. Normally you know that whenever a computer is connected to a telephone line, there will be a device sitting there called a modem. Now this modem is something which will convert the digital data to analog signals. So modems are something which and similarly at the other end, the demodulator part of the modem will convert the analog signal, from the analog signal convert back to the digital data. That is the second category. The third category is analog data and digital signals. Now what is analog data and digital signals? There is a data as such as analog, so say music or something like that, and the signal is digital. Okay. So now an example of this would be, for instance, you have a sound card in your system. Now what does a sound card do? In the sound card, let's say you are recording something through the microphone. Through the microphone, an analog signal is taken in, recorded, but it is stored inside in digital form. So you can see that the signal that is used to store that information is a digital signal. So it's an example of an analog data being converted to a digital signal, and you may use these digital signals to transfer these data from one place to another. So it will be an example of analog data, digital signal, and the job of a codec, which is normally sitting on your sound cards, is to convert from analog data to digital. That is, it codes the analog data into digital data, and similarly decodes from the digital signals back to the analog data. So that's why we refer to it as a codec. It's a coder cum decoder. Okay, so that is the third category. The fourth category is where I have digital data being transmitted directly as digital signals. So again, example of digital data could be data coming from a computer, a file for instance, and let's say I am transmitting data from one computer to another computer through an Ethernet cable. There you will find the signaling is done actually as digital signals. So digital signals are transmitted, and these digital signals carry the digital data information that needs to be transmitted. So these are the four different possibilities that we have. Now that we have the four different possibilities, there are different methods that are used for each of these possibilities. But before we look into those methods, let us look at what do we normally mean by certain things like analog transmission, digital transmission and so on. It will kind of make things a little more clearer. So let's look at analog transmission first. Now what do you mean by analog transmission? That is, the signal that is used is analog, so the transmission that is taking place is an analog transmission. Okay. So when we do analog transmission, there are two things that we need to do. We need to do modulation at one end and demodulation at the other end. So what is meant by modulation? Modulation basically is converting data signals to a different form. The data is available, it is to be converted to a different form, and typically we are looking at, if you are looking at analog transmission, it is going to be converted to an analog form. Okay. And the signal that is being modulated is called the carrier signal, and this carrier signal is the one that is going to be carrying the information for you. So it is called as a carrier signal, and some characteristic of this carrier signal will be changed. So it's called, which is why we call it as modulation. Modulation basically refers to some change. You are changing something in that carrier signal so that it represents the data. So this is what we mean by modulation. Demodulation. What is demodulation? Demodulation is the reverse process. That is, you now have to recover the data signal from the modulated signal. So recovering the data signal from the modulated signal will involve taking that modulated signal, doing some operation on it so that you are able to get back the data signal. So this is what we need to do. So here again we talk about analog modulation versus digital modulation. So what is analog modulation versus digital modulation? Analog modulation would mean that I have an analog data coming in being converted to analog signal. Digital modulation refers to digital data coming in but being converted to analog signal. In both these cases, the end signal is analog. That is what we need to remember. So next is digital transmission. So when you look at digital transmission, we are transmitting digital pulses. Actual transmission of digital pulses takes place in digital transmission. The digital data that is transmitted, it could be transmitted as such, or it can be encoded and transmitted. That is if I look at digital data, because digital data is already in a digital form. So if that digital data needs to be transmitted, I may be able to transmit it as such, or I may have to encode it, which means I kind of slightly modify to a different form and transmit it. This is one possibility. But if I have analog data that needs to be transmitted, now analog data obviously is not in the digitized format. So the analog data should be digitized or converted to digital for transmission. So here this is where we said we will do the job of coding the data. So we talk about coding the data so that it can convert the analog data to digital, and then you decode the data is getting back the analog signal back from the digitized data. So this is what we refer to as coding and decoding. So when we talk of analog transmission, we talk about modulation and demodulation. When we talk of digital transmission, we talk about coding and decoding, and we talk about encoding and so on. So these are the major two categories that we have for transmission. Out of these two, when it comes to data being transmitted, typically we are looking at digital transmission, that is as most of the communication systems today are digital. There are also analog transmission systems are still used. So we will take a look at how digital data is taken and converted to both analog transmission and digital transmission. So this is what we have in terms of what needs to be done for transmission. Okay. So next let's look at how these signals propagate down the line. Now we have signals. We know that they could be analog signals or digital signals. Whatever be the signal, let's look at what actually happens in terms of propagation of the signal. Now what do we mean by signal propagation? The signal is going to travel down the link. Okay. Now when you look at any signal, you can look at the signal as a signal of a certain frequency. Let's say for instance a sine wave. If you take a simple sine wave, you can look at that as a signal which has a particular frequency. And any of the other signals also can be represented as a set of sine signals or sine wave signals, sine wave forms. So which means I can look at any signal being transmitted as a group of sine wave signals being transmitted. So now when you have different frequency signals being transmitted, each of them will take different amounts of time to propagate down the line, down the link. Okay. So this gives rise to what is called as propagation delay. So what is propagation delay? You know that always, we know our time distance speed formula. So propagation delay is link distance divided by the speed of the signal. Okay. So time equal to distance by speed. So we know that. So in this case, the distance here refers to the entire distance that the signal needs to travel, which is the complete link distance, and speed of the signal, that is the speed at which it travels. And propagation delay will be equal to link distance by speed of the signal. Now here again, depending on the media that you will have and the kind of signaling that is used, different amounts of time are taken for this propagation delay depending on the speed at which it travels. Suppose we take optical fiber. Now for an optical fiber, the speed of the signal is the speed of light because it is light that is being transmitted. So 3 into 10 power 8 meters per second. So for copper cable, approximately it will come to 2 into 10 power 8 meters per second. So if I take a link of 10 kilometers, you can see how much of time it will take for the propagation to occur. So propagation delay on a fiber cable for a 10 kilometer line will be 10 kilometers divided by 3 into 10 power 8 meters per second, which will be 33 microseconds. On a copper cable, it will be 10 kilometers divided 2 into 10 power 8 meters per second, so it will be about 50 microseconds. Okay. So you can see how the propagation delay will vary depending on the cable that you have. Now obviously you can see that if the distance varies, naturally the propagation delay will vary. So these are two factors we need to understand when we look at propagation delay. Okay. So we will take a short break now and resume after the break. Welcome after the break. So we were just looking at what is meant by analog data, analog signal, digital signals, and we also looked at what is meant by propagation delay, that is the time taken by signal to propagate down a line. Now the next thing that we need to look at, which are issues that we normally talk about with respect to the physical layer or with respect to the data transmission as such, is noise. Noise is something that we always hear when we talk about the physical layer. Now what is this noise? It's any unwanted interference with the signal. That is what we mean by noise. Now there could be many sources of noise. We have something called thermal noise, which is inherently present due to the agitation of electrons. Because of the agitation of electrons, there is always some amount of electrical noise which is created, and this noise could interfere with your transmission, because after all it is some electron, some flow that is happening, and then this kind of a noise will interfere with the transmission. Other than this, there could be some external interferences. Now external interferences can happen due to things like lightning, signals in adjacent cables. You may have a group of cables that are used, that are tied together for carrying lots of data. So when that happens, signals in adjacent cables can interfere with one another. When that happens, naturally there will be some interference. So this kind of external interference can cause a lot of problems. For instance, if you have a lightning is a very high intensity electrical signal that comes about, and that can come and totally destroy the data that is being transmitted. So this is something that we need to watch out for. So these are external interferences that we will have to deal with. Third thing that you can have is different channels being carried on the same medium. For instance, you have the same medium, but you may have different channels being carried on it, say at different frequencies. Each frequency may be carrying data corresponding to different people. Okay, so in which case what can happen is sometimes data from one frequency may overlap with data on another frequency, and that again can cause some interference. So we need to be careful about these. Some of these you can see are man-made, some of these are external, and some of these are design-made. That is, when you do the design, if you have not done it properly, then you get into trouble. So we need to be careful about handling these different types of noise. So let's just look at a little bit more on this. Now how do we understand the effect of noise? Noise is normally captured, the effect of noise is normally captured as signal to noise ratio. So what is the signal to noise ratio? Signal to noise ratio is the signal power divided by the noise power. What do we mean by signal power? That is the power of the transmitted signal over the power of the noise signal that is there. So now when you talk of signal to noise ratio, it is normally calculated in what we in a measure called decibels. Now what does the decibel stand for? It is defined like this. You define it as 10 times log to the base 10 signal power divided by noise power. So this formula that you have here gives us the SNR, the signal to noise ratio, calculated in measured in decibels. Now you can easily see that the SNR should be high to recover the signal in the presence of noise. If the SNR is not high, you can see the effect of that. When I say SNR is high, it means the signal power has to be much larger than the noise power. If the signal power is larger than noise power, the signal power will subdue the noise power and you will be able to recover the signal. But if the noise power becomes greater than the signal power, then recovering the original signal becomes difficult. So this is the problem that we have with respect to noise. So you can just see a visual effect of what happens with signal and noise. You have a signal that's given over here. On this signal, if a noise of this particular kind is imposed on it, then you will find that the resultant signal will have signal component plus the noise component on top of it. Sometimes the noise component may be so powerful that you can't even recognize the signal. Sometimes you will be able to recognize the signal, and your electrical system, your receiver, must be able to distinguish between the signal and noise, remove the noise and get the signal in. So this is what we expect. This is the expected behavior in a transmission system. In the presence of noise, we need to be able to remove the noise and get the signal out. So that is our expected behavior. Okay. The third thing that we look at with respect to issues in transmission is attenuation. Now what is meant by attenuation? It's the reduction in the strength of the signal as the signal propagates down a link. That is, when the signal propagates down the link, there is some power that is lost or power that is consumed. You can look at it either way. So because of that, the strength of the signal keeps reducing. So the strength of the signal keeps reducing, then you transmitted a particular power, but you receive a totally different power signal. So what happens in that case is, we say that an attenuation of the signal has occurred. It has attenuated. And this attenuation again can be measured in decibels, because we are just looking at the ratio of two powers. Now what is the ratio of two powers? We are looking at the transmitted power over the received power. So I am transmitting at a particular power, okay, which is the transmitted power, and I have a received power. I am receiving, say, some other value there. So let's say I transmitted 100 watts, but I received only 50 watts. So you have 10 log to the base 2. So that will be a 3 dB drop in the signal strength. So we say that the attenuation will be 3 decibels. So this is the way we measure attenuation. And here again we remember that if the attenuation value is very high, it would mean that the transmitted power, if the transmitted power is very high and the received power is very low, then we have a problem. then there is a lot of attenuation. So that is something to bother about. So this is something we have. Now if the attenuation is very high, as I said, the receiver may not recognize the signal at all. So that is again another problem that one has to deal with. Just as we said in the case of noise, if the noise power is very high, you may not recognize the signal. Similarly, if the attenuation is very high, the receiver may not recognize the signal, which may result in the loss of data. In that case, what we normally do is we use repeaters and amplifiers to boost the signal strength. That is, over a particular distance, you find that the signal strength has dropped to a particular value. Then we use devices called repeaters or amplifiers over there. Amplifiers are used when you are using analog transmission. Repeaters are used when using digital transmission. So these repeaters will repeat, that is, they will remove the data from the signal, again construct a new signal out of it and transmit the data, which is why it is called as a repeater. An amplifier, on the other hand, will just bring in whatever data is coming in along with whatever signal plus noise, whatever is coming in, the whole thing will just amplify it, just raise the signal strength and transmit it. So this is one of the distinctions that we have between an amplifier and a repeater. So repeaters, you can see, are much more powerful in the sense that they are less susceptible to noise, because they will remove the noise, reconstruct the data and repeat the whole process again. So that is why we have a repeater. So when you have attenuation, you can see that in this picture, you can see that an attenuated signal is again boosted in strength by the repeater and transmitted out. Next thing we need to look at is what we mean by the capacity of a channel. Now given that you have a certain amount of attenuation that can take place, given that you have a certain amount of noise that is going to be inherently present in a system, how do you determine that so much of data can be carried by my communication channel? Okay. Now here there are a number of people who worked on some very interesting results. So we will just take a look at one or two of these. So what we want to look at here is, we want to calculate the data rate. Now data rate typically is measured in bits per second, given that you have a certain bandwidth for a channel and that there is some amount of noise. So that is, we need to find out the relationship between the data rate and the bandwidth of the channel. Now it has been found by a person called Nyquist that data rate and bandwidth are directly related to each other. Now let us look at what is meant by bandwidth of the channel first. Now bandwidth of a channel is the highest frequency minus the lowest frequency it can carry. Now remember that every single transmission media that we use has its own characteristics in terms of its bandwidth. That is, it will be able to carry only frequencies of a certain frequency. So the highest frequency it can carry minus the lowest frequency it can carry is referred to as the bandwidth. So with the given bandwidth, what we are interested in finding out is, given that this is my bandwidth, say W is my bandwidth, given that my bandwidth is W, how much of data can I transmit? This is what we need to identify. So here we have a very interesting result which is referred to as Shannon's formula. Now what this formula tells us is, given that I have an SNR, a signal to noise ratio for a particular channel, and W is the bandwidth of the channel, it gives me the capacity of the channel in terms of these two figures. So C is given as W times log of 1 plus SNR. Now SNR here is not measured in decibels but measured as a ratio. So as a ratio, if I have SNR or signal to noise ratio 1 plus SNR, I calculate, take the log of that and multiply that with W, which is the bandwidth. So W times log of 1 plus SNR gives me the capacity of the channel. So this is a formula that is used to identify how much of data rate can be supported on any given channel. Okay. So, so to summarize, if we look at what we have covered in today's lecture, we have looked at data and signals, we have looked at analog data and digital data. Similarly, we have looked at what is meant by analog signal and digital signal. We also distinguished between analog and digital transmission. Now remember that when I talk of analog and digital transmission, we are basically talking about the signals being transmitted being analog or digital. And with respect to the challenges faced, there are two, three things that we looked at. Important one among them is noise. And when we talk of noise, we need to understand that we measure noise in terms of signal to noise ratio, and the signal to noise ratio has to be high in a system. We always need to design systems such that the signal to noise ratio is high. And we looked at signal to noise ratio, we also looked at how the signal to noise ratio can be used in order to determine the capacity of a given channel. Depending on the bandwidth, using Shannon's formula, we will be able to estimate the amount of data that can be carried on a signal. In addition to this, we also looked at what is meant by attenuation and how repeaters or amplifiers can be used to boost the signal strength. So these are the basic facts that we need to understand about the physical layer. What we also need to understand is how this data gets modulated or coded into digital data or analog, how the analog or digital data get converted to analog and digital signals. That will be a topic of a subsequent session, but in this session we just have got the basics of how analog and digital transmission take place. Now you should also be ready to answer a few questions. Okay, one of the things that you need to understand is what is the difference between analog and digital signals. This is a question that you should be able to very easily answer. The second question that you could answer is what are the 4 possibilities that need to be considered for transmission. The third question is what are the different types of noise. We saw that there are different types of noise, you must be able to at least identify the different types of noise exist. So how do you determine the amount of data that can be transmitted? These are 4 simple questions which cover the various topics that we have looked at today. So with this, I think you should be in a position to understand the basics of the physical layer. Thank you.